Hi, we're Group 15, and our final project is on AI generated image detection using CNN architecture. My name is Lyndon Pham,
I'm Adam Pecoraro.
And I'm Sean McClellan.
and let's dive on in. So, the problem statement and motivation. So, in today's world, we have seen that there's an ease in creating hyper realistic images using generative AI models. The risks with these are misinformation, copy infringement, deepfake content, and other malicious uses. So we wanted to mitigate these risks by deciphering between the real and generative images. So we will be creating an AI generated image detector using CNN to determine the digital image authenticity. So the data that we were using is a Kaggle data set. They have 79,950 JPEG images, 93.7% for training, and then 6.3 for testing. Uh, it contains 768 by 768 pixels. We have reduced it down to the max of 384 by 384 pixels, three color channels, and the image format is going to be in JPEG. For our output, we wanted to determine if the image is AI generated or not, and the output a binary signal which classifies the image, which zero is going to be not AI generated and one being AI generated. For data augmentation, the techniques that we are using are flip, rotation, brightness, jitter, noise, and normalization. And then for our baseline model, we were utilizing ResNet 50 and adding on our own fully connected layers and like a classifier to produce a validation accuracy of 91.11%. As you can see at the bottom left, with that image, that is human, and then for the right, that's going to be AI generated images.
In terms of our model architecture, we did use ResNet 50 as a feature extractor, and we use a little bit of transfer learning from that, which heads into our convolutional 1D layer, followed by batch normalization and a residual layer. All of this gets fed into a global pooling where we flatten the data and then connect it to a series of fully connected layers and dropouts to increase generalization before heading to our classification layer, which brings it down to our two possible outputs. And for optimization, we are using SGD. In terms of evaluation, we're pretty happy with how we turned out. We had an F1 score of 98.29% and an accuracy of 98.28%. Our model does very well at perceiving real images versus AI generated images. And in terms of improvements moving forward, in order to get our accuracy even higher, we think readjusting data augmentations for better performance and implementing a scheduler to impact the learning rate would help improve our accuracy. In terms of the comparison to our baseline model, as stated before, our baseline model architecture was a ResNet 50 with pre-trained weights, and we appended a custom classification layer to that and trained that layer. This baseline model had a testing accuracy of about 90.18%, so nearly 8% increase when we added in the complexity from our current model. The F1 score also went up about 6%, which is pretty impressive in terms of improvements there. So overall, we did find that the current model architecture outperforms our baseline model with almost every metric except for training time. And training time is, of course, impacted by the increased complexity of our custom model.
All right, so to go into some more depth for our results, we have here is a basic classification report where you can see that we have about 2,500 human images and about 2,400 AI generated images, where they have an average results for F1 score of 98% for each one, and along with the human generated having precision of 99% with a recall of 98, while AI had a precision of 98 and a recall of 99. And for our confusion matrix here, as you can tell, we did a pretty good job here. You can see there's really only about 50 images for that were predicted wrong for either being human generated or AI generated. And as you can see here, an example of on the left side here is a AI generated image that was detected to be human generated. And then on the right side here, we have a example of a human generated image that was detected to be AI generated. Now, for some more continued results for generalization, we think we did pretty well, as the difference between our training accuracy and our testing accuracy was only about 80%, not 80, 0.8%. And to achieve this, we really believe it's due to our advanced feature extraction from Resident 50, the dropout layers we had, and just having a very robust training set. Some limitations that we did come across were that a convolutional 2D layer was actually really yielded worse results by about 0.5% in accuracy. And we think this is due to mostly overfitting caused by unnecessary complexity from the convolutional 2D layer. And then this is just some references for our Kaggle data set and then for transfer learning. And thank you for listening to our presentation.